Hi everybody, welcome to Mrs. John's lesson. This is for year 13 physics, modern physics, and this is the Bohr model of the atom and to explain the hydrogen electron energy levels. Now, the reason why Bohr came up with this model is following on from the spectral lines that scientists saw, and we saw in our last lesson that, when you look at white light through a diffraction grating, what you see is the whole continuous spectrum with blue on one side and red on the other side. However, if you look at the color emitted by a gas which is at low pressure in a tube, what you see is not the continuous spectrum, but you see definite spectral lines. Now, it could be an emission spectrum or an absorption spectrum. It all depends how you're looking at it. So if it is looking at light emitted from a gas under low pressure, exposed to high voltage, what you can see is an emission spectrum, which is a black background with definite colored lines. If, on the other hand, white light is made to pass through a gas and then you look at it after it's passed through a particular gas, what you will see is an absorption spectrum, which is definite black lines on a colored background. Now, when you compare these lines for a particular element, you find that the lines on the emission spectrum corresponds or matches the lines on the absorption spectrum. So what's absent in one is present in the other. Now, every element has its own signature spectral lines. And so we've come up with, and we learned about the Lyman series, the Balmer, the Paschen, the Brackett and Pfund series. And what Balmer saw was these lines. He studied the hydrogen spectrum. He only saw 4 lines, and he came up with an empirical formula to calculate the wavelength of these lines that he numbered 3, 4, 5, 6, 7. He only saw 4 lines, so he numbered them 3, 4, 5, and 6. And the formula that Balmer came up with for the wavelength was 1 over wavelength is Rydberg's constant over 1 over 2 squared minus 1 over L squared, where L is the line number. And later on, when they found other series, they came up with a generalized formula where instead of 2 squared, they substituted it with S squared, which is the series number minus 1 over L squared. And this is the formula, the empirical formula they used for wavelength. And then if you want to find the frequency of a particular line, what you can do is you use the equation C equals F lambda, which is the wave equation where C is the speed of light, which is 3 times 10 to the power of 8 times is equal to frequency times wavelength. And then you can get the frequency is this 1 over wavelength times C. So this becomes CR 1 over S squared minus 1 over L squared. Okay, so why does this happen? So Bohr came up with this theory, which was following on from Rutherford. So according to Rutherford, he said that the atom, with his experiment with looking at the gold foil experiment, where he said that the atom consists of a central nucleus, which is positive. He called the positive particles protons. Chadwick discovered the neutrons, and to say where the electrons were, Rutherford said they actually just go around the nucleus. Now that's where it didn't quite match up, because if the electrons are going in a circle, then they're accelerating, and theoretically they should lose energy and collapse into the nucleus, but this does not happen. So what Bohr said was, yes, you have your central nucleus, but what happens to the electrons is that the electrons occupy different energy levels. These are called energy levels or quantum states, and these are discrete. They have definite values. And he called these energy levels are numbered. So the energy level closest to the nucleus is the lowest energy level. It is given as n equals 1, and it's also called the ground state. The level just above that is called the first excited state, or energy level 2 and 3 and 4 and 5, and it can go on to infinity. Now he said that the electrons can occupy these energy levels, specific discrete energy levels, and in order to go from one energy level from a lower energy level to a higher energy level, they have to absorb a photon of energy which is equal to the difference of energies between these two levels. Now, in order to find out what is the amount of energy that is required by an electron to go from one energy level to the other, or to fall from a higher to a lower energy level, that's when it gives out a photon of energy, is given by this equation. So you've got the frequency. Now we know that the frequency of a photon is given by, it's related to its energy by hf. So the energy of the photon that is given out or absorbed is given as h, and this is the times for frequency. So you get hcr times 1 over s squared divided minus 1 over L squared. Now, and the energy at any level, at any particular level for an electron is given by CHR over n squared, where n is the quantum level or the quantum state. Now, what we need to know and to remember that so long as the electron is bound to the nucleus of the atom, it has negative energy. And you think, how can energy be negative? Well, the energy can become zero if it can leave the atom, and if it has positive energy, it'll have kinetic energy to go beyond. Okay, so as long as the electron is bound to the atom, it has got energy, it's got negative energy. The important thing about Bohr is that the energy of an electron is quantized, or it's given a discrete value, and it can only occupy those values and never any values in between. And to go from one energy level to the other, it has to absorb a photon of energy that is equal to the difference in energy between these two levels. Electrons don't remain in the excited state for too long. They fall down, and when they fall down to a low energy level, it gives out a photon of energy or light or radiation that is equal to the difference in energy between these two states. So what does the S and L stand for? S is where it falls down to, the series number, and L is the line number, whatever it's falling from. And the series number, if all energy level drops to level 1 are the Lyman series, and they're all in the ultraviolet part of the spectrum. All energy level drops to level 2 are the Balmer series, and they're in the visible part of the spectrum. All photon drops to level 3, 4, or 5 are your Paschen, Brackett, and Funch series, and they're all in the infrared part of the spectrum. So I'll make another video to explain and tell you how much the energy is at each of these levels. So bye for now, and I hope that made sense.